Liam Randall, who is, aside from being one of the organizers of this event, he is a managing partner at Bro IDS, and so part of the Bro core development team. Bro is his lifeblood. It is his bread and butter. It is lays in bed with him at night and snuggles him close. Liam is speaking, and me. If only I was Bro. Liam has spoken, I'm so glad that's screening online. Liam has spoken at ShmooCon, he's spoken at Nova Hackers, at the Bro Exchange. He's been on paul.com. He is a worldwide, globally known resource for network security monitoring for Bro IDS, and as a general technologist and consultant in terms of network security and training. Just a fantastic guy, works crazy hard, has put his so much effort into this thing and into developing the information security and community in general. So really, really, really happy to have him here speaking to us. Liam Randall.
Thank you for the wonderful introduction. So,
thank you for the wonderful introduction.
Hey, thank you. So this is the team that I'm on. I like to point out that Bro's been around for a really long time. The National Science Foundation has been involved in the funding of Bro for close to 20 years, and we actually just had the funding renewed out of the International Computer Science Institute just this last fall, another 3-year up on the work. Bro began a long time ago, and in Vern Paxton's original paper, he called it Bro as an Orwellian nod to the Big Brother type potential of the platform. So real quick, I wanted to do a couple shout outs. I'm at Hectaman on Twitter. If you'd like to live tweet this event, you could tweet to hashtag BSides Cincinnati. And I wanted to do just point you guys to people that are interested in security to a couple of local conferences or conferences you should check out. Circle CityCon in Indianapolis is coming up shortly and looks to be an amazing event. BSides DC is not only an incredible event that is held in the fall. I'll be teaching Bro classes there, but they also contributed or loaned us all their cameras and gear to help kick off BSides Cincinnati. So we owe them a huge debt. And they loaned us their man whore Brett to do videoing. ArchCon in St. Louis, more Bro classes there, is going to be outstanding. This is basically becoming NSMCon. So if you have interest in network security monitoring, this is going to be the place for it. I'm teaching, Hanashi's teaching, Baitlick's going to be there. It's going to be a world-class crew. But so let's get to today's topic. And today's topic is simply reconnaissance detection. In theory, somewhere. So this is what we're going to look at today. We're going to start by talking about why reconnaissance. And then we're going to look at some specific types of reconnaissance for DNS, HTTP, SSL, Classic. And then we're going to take a case study and understand why detecting reconnaissance can really give you a leg up on your network. One of the things I love to see Dave talk is that a lot of his techniques are incredibly simple. And he constantly focuses on that people just aren't doing the common, the obvious stuff. Ultimately, at the end of the day, there's one real difference between defenders and attackers. And attackers know when their techniques work. It's this common problem that we have as defenders in that we only have to slip up once, where an attacker only has to get their solution to work right. We never are 100% sure that our solutions are working. So we try to take a methodical approach with the Bro platform in developing tools for incident responders to use. So one of the techniques that I lead up is I spend a lot of time actually pen testing networks, generating sample traffic, and then we develop heuristics and tools and frameworks to detect those. So today this is part of my work on the reconnaissance framework. But first, let's talk about why you would want to detect reconnaissance to begin with. When you look at today's threat environment, Dave's approach to a problem is actually very similar to what we see out with real threat actors. A group of pen testers got together and formed something called the pen test standard. And the idea was to come up with a standard that allowed people to say, this is a good pen test, this is not a good pen test. And it essentially enumerates a large number of things that need to be done when you're pen testing networks. So there are various approaches to the problem, and it involves a whole lot of steps. But the first step is always reconnaissance. It's essentially what you begin your network with. There's open OSINT, which is not really something that we're going to be addressing today. There's HumanInt, but all of those things are outside scope. But anything that is active that touches our systems either directly or that we can detect through a derivative heuristic, we can go ahead and apply that to interdicting adversaries at the earliest possible time, when they are initially starting to look for targets of opportunity in your network. These attacks, at some level, when we start to look at them, stand out like a sore thumb when you have the right tools deployed in your network. And what we'll do today is we'll start looking at some various sample attacks, and then we'll look at some of the major successes that we've had in the Department of Energy with the Bro platform. So this is what you're looking at with pen testing. You essentially want to know your customer like you know thyself. So the part that we're actually looking for, if there are other people that are interested in learning about this, a great way to find interesting topics to explore is start with the pen testing standard and go through and pen test your own network. Start doing this reconnaissance and see what bells and whistles you start tripping up in your network. There is a more common known or an as commonly known process that's referred to as the kill chain. If you look at the kill chain, I actually have a talk for each one of these steps. Today, this is the talk for just the first step. And I think this is probably the most important and the most often overlooked, because so many of the reconnaissance techniques that we see are beyond 2 standard deviations outside of normal. They're 3, 4, 5, 6, 100 standard deviations out, the type of behavior that you'll see threat actors participating in your network. So, excuse me. So today we're going to approach this through example. So what I've done is I've basically started with the most basic type of reconnaissance. So this would be horizontal sweeps and vertical sweeps on a host. Then we've added in some protocol level reconnaissance where you're actually in DNS and monkeying around. And we'll look at PCAPs for that. Then we'll look at some for HTTP, SSL, and really then try to tie it all together. So who here has used Bro? I know you guys have. This is awesome. This is way more people than had used Bro last year at this time, which shows that we're starting to get our message out there. So the hardest part about really understanding what Bro is really just this first approach. It is essentially a fundamentally distinct and unique approach to this problem. You start by installing the Bro platform, which are the daemons and the protocol analyzers that you spin up on your network that can be used to scalably intercept the traffic that's on the wire. On top of that, there is a Bro programming language that is a domain-specific language, a language that's designed for working with network traffic. You could think of it as a Python for the network. It is specifically designed for monitoring and all of the associated types of topics and tasks. And then on top of this, you simply install applications. So think about intrusion detection has been our bread and butter for a long time, but with this kind of insight into your network and protocols, things like monitoring, vulnerability management, data loss prevention are all certainly within the wheelhouse of Bro. So Bro is made up of 3 layers when you install it. So what does a deployment look like? What we're essentially doing here is we're saying, what is the weakest part of the network? When you think about all the different things you can install for monitoring in your network, you might have agent-based technology. So you're going to go to Microsoft or Symantec and you're going to buy something and install it on all your stuff, right? The problem is that what makes the internet work is the ability to have protocol interchangeability. So that so long as we've standardized, and this speaks HTTP and my laptop speaks HTTP, that's how the whole internet works on everything. And when we look at this growth in the Internet of Things and cloud computing, you essentially are getting large numbers of devices on your network that are not under your control, that are poorly managed, that do not have agent-based technology. So we think our model is that we intercept the protocols on the wire. And if you're speaking a language that we understand, a protocol, then we can tell you everything about that. You have access not just to that rich protocol metadata, but also all of the contents of all of these flows, and at scale. We're turning on our first cluster at 100 gigabits per second next month. That's fast. That's 100 in each direction, by the way. So what does Bro do? So one of the most common scripts that people run is to write protocol logs. So every time we see a protocol that we understand, we're going to write a very detailed, highly structured log. But Bro is not these logs. All of this data is available in the programming language in real time as it happens. And you can build these little Bro apps around this data. But these protocol logs are essentially, think of it like a forensic record. The Army calls it the ground truth of the network for each protocol. So if if you think about full PCAP is 100% of the traffic, the actual conversation. Bro logs would be 1% or 0.5% that describe a flow in a very, very detailed way, that give you, as an analyst, usually enough context to understand what was going on. The second thing that we try to do is we write these alert logs. So a protocol log would have all the HTTP, not just the HTTP on port 80. It's dynamically detected, it's IPv4, IPv6, it's any port, it's any tunneling configuration that you've got stacked up. An alert log will be, hey, we noticed something over here in these protocol logs that looks weird. Here's a notice, right? We saw maybe 20 NX domain lookup failures in DNS log. So DNS log will just log everything that's in there, right? Just writing it all down. The notice log is where it would tell you something about it. There are also a whole series of meta logs, things like files.log, which is literally just a record of every file we see. Do you give a crap what protocol it was? If you do, that's logged right there in that log. But that's that kind of approach that we're taking with those meta logs. The final thing you can do with Bro here, and this is when we get to our case study at the end, is by far the most powerful, is actions. Bro's a programming language. So if you want to pivot out to your network infrastructure or to a sandbox or an outside database, those things are all very easy to do. And many of the most powerful integrations that we ship out of the box for free with BSD licensed Bro are all of these integrations with third-party providers. So when we talk about Bro for security, because for this reconnaissance phase, this is essentially a security auditing use case, we're essentially talking about an approach to intrusion detection. If you have academically studied this topic, there are two classic approaches to intrusion detection. There's signature-based detection, which is how most products work. It's essentially, let's find the bad things we know about. Let's give me a list of known bad IP addresses, file hashes, byte offsets for particular pieces of malware, known bad URIs. If there's anybody that's here from the military, anybody familiar with like anomaly detection at scale, you deploy Silk or Argus, and you're essentially going to use mathematical models, create a Markov chain, and say, well, this is a web server in my DMZ. It should produce 9 times as much content as it receives. If I find somebody that's violating this ratio, let's go ahead and investigate it further. Bro absolutely can do both of those things, but what we're going to look at today is this third approach, where we use the flexibility of the Bro programming language to build intelligence into the network. Has anybody heard of Dan Geer? We know him? He is possibly the brightest guy in our space. He's the CIO at In-Q-Tel, the CIA's investment wing. And he has this amazing talk that you should look up later, or right now if I get boring, and that he did at Spoots and Souks last year. And he essentially talks about this growing curve, right? The growth of the internet and how we're all essentially screwed. He's like, we have 3 choices, right? We can stop growing, we can grow security people at the same rate, neither of those two is going to happen, or we can start to build intelligence into the network, right? And when we as tool builders approach Bro, we really try to keep that in mind. We try to give you the flexibility to do the things that you want to do easily. We sometimes joke about that we're building C3P Bro, right? It's a protocol analyzer with a bunch of logic on it. That was a totally failed joke. All right, laugh at the failure though. I'll take it. I'll take sympathy. All right, so let's start by looking at some real examples here. Let's get down to the meat of it. So the first example we'll talk about is just simple, TCP, UDP, ICMP probing, right? This is actually reasonably easy to detect. There are many systems that will tell you that, hey, somebody just did a horizontal sweep across my network and said, are you running MySQL? 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 These would be things that we commonly see like SIP vicious running or SSL scan or mass scan. Rob, Graham, if you read this, slow it down on rolling out stuff like Heartbleed, killing us. So let's actually look at what these things look like on the wire. When you're thinking about from a log perspective, let's actually look at some traffic. I think that's the most instructive here. All right, so this is basically a host scan. So this is the connection log. So this is the basically if you think about your TCP/IP cake here, this is the bottom layer. And this also includes tunnels. Like let's say we find a connection that's in a Torito tunnel or a GPRS tunnel. We'll pop that tunnel and then drop this new connection in here. And you can actually, if you care that something was tunneled or it was in my parent's parent, there's actually a little tunnel column here. So think of these things as like Excel spreadsheets here. And this is the sort of just the connection layer of what's happening. Now you'll notice we are doing, dynamic service detection. And if there were any protocols in here, there's not, because this is just, oh, there was a DNS request. You'll see that you'll get it tagged out here. These other fields kind of tell you that this was a S0 was attention connect seen but not established, right? So this is a regular SYN scan. So pretty easy to detect. So we can actually do these kind of detections at mass scale. This would be a sample notice that would fire. Okay, so this is pretty common. Lots of things can do that. You essentially, within Bro, we're going to look at actual code examples in a minute here, but you're essentially just going to start counting all of the things at scale. So another example, though, this one is actually something that other systems cannot do. So here what we have is we have a trace routing going on here. So when you think about what you're doing with a trace route, you're essentially changing the TTL on the packet so that they expire and you get a notice back. So you can use it to map out what are all the devices between point A and point B. So this is actually very complicated. I don't know of any other systems in the non-classified space that can detect trace routing. And so let's look at what this would look like in Bro. So we see these trace route detectors, and these are things that ship with Bro out of the box right now. If you go to our website and download Bro 2.2, we're actually going to have a baby soon. Bro 2.3 should be delivered early next week by cesarean. It's been somewhat of a painful baby. But you'll get this notice that says someone's running trace route. We actually are quite terrified running this at places because there is far more trace routing going on in the network than I think most people are aware. This is something that's commonly not controlled at your firewall. Blocking ICMP packets will sometimes break the functionality of many applications. If you're a gamer, for example, a lot of them will do these checks back to try to tell you about what's going on in your network. There are threat actors that are using ICMP as a C2 channel. So this is a great way to get a little insight and find out what's exactly going on. All right, well, that is those are neat, but let's go deeper. We can always do a little bit better here. So let's start stepping deeper into protocols. Actually, let's talk about the library first. So how do we count these things? Essentially, when you're handling something like traceroute, it's a worst case policy. When you're tapping networks at scale, what you essentially do is you start mapping traffic to CPU cores, and CPU cores have processes running on them. So when you think about how do I detect traceroute, you have to realize that each one of these packets can go to a different process in a point in time. So in our model, by default, all of our little Bro workers are friends. So we're using things called summary statistics, and this is actually a very huge idea that we're doing in Bro that I think most people are not understanding. And I think that means that we're not communicating it very well, that we need to do a better job explaining what the real sexiness here in this model. So who's heard of MapReduce? You guys heard of that? You don't have to use it. You've heard of MapReduce, right? If you don't know what it is, you understand that it's this idea, this approach to a problem that lets you handle big data, whatever that is. So when you look at what we're doing with Bro, this is a sample Bro box here, right? You take a couple servers or one server and you map traffic to CPU cores. We load balance on a 5-tuple hash. So it's the port, IP address pairs, the port pairs, and then the service. So these load balancers will direct all the packets from a single flow or a conversation to an individual CPU core that's running an individual Bro worker. So this one Bro worker can see all of the things that we say in one conversation. But when you think about things like HTTP or even the traceroute example, they're not stateful protocols. So the first reconnaissance piece could go to Bro worker 1.1 up there, and then 3.4 down here could get another piece of that packet. So in our model, all of our little Bro workers are friends with each other, and they can all talk and share data. So summary statistics is the way that we start sharing data between all of these workers. So it is essentially a generic library for doing MapReduce on data in motion. That is a huge idea that other tools aren't designed. They have a different approach to the problem space. Our workers were already friends. So for them to all start counting together and holding hands was just a natural next step. So when you think about handling these problems now, what you're probably doing is you log all the things, and then you package it up, and you ship it off to Splunk, and then you do some analytics out here because this is where I do big data. Streaming, the streaming library in Bro allows you to take these measurements in real time on your network. right? That's a huge idea. You can start saying, well, let's just count all of the, like Dave's example, I think he mentioned that he exfilled 16 terabytes of data from a single host, right? So one summary stat that you may run on your network might be, let's just count the bytes leaving the network by host. And let me know if anybody transmits more than 100 meg out. Pick some arbitrary large threshold to reduce the false positive on your network. Those are the things that you can start to do with this technique. Today we're going to apply this technique just to reconnaissance detection. But when you're building these things, you have a couple tuning points. You essentially have an epoch, which is a period of time, and it has to be a streaming measurement. So it has to be a measurement that you can take when I have all my data in my hand here. You know, we don't block and bro. So you do everything you have to do with a piece of data and then you let it go because it's not coming back, because you can't do that at big scale. It has to be composable. So what does composable mean? A composable measurement just means that, think of all those bro workers, that they can all take a share of the measurement and then you can reassemble it upstream. So let's say that Brett and I wanted to take the composable average height of all the people in this room. And Brett is fresh and he's much more efficient. He measures 50 people's heights and I measure 30 people's heights. The composable average height would be 50 times his number plus 30 times my number divided by 80. That's a composable average. So for all of the different measurements that we can take, like the composable average, the composable sum, the composable min, max, all of these other measurements that are in the library, we're implementing these with these various composable algorithms. And there's a composable version of essentially everything out there. And then finally, you get to decide whether you want to take a true measurement, which would say, okay, count all of the, the top 10 DNS hosts for each client on my network. Or you could take them in a probabilistic fashion. And a probabilistic data structure is something like hyperlog log or top K. It's basically this mathematical construct that allows you to, with a very high degree of precision, start to say things like, count these things and be really, really, really close to the answer. And those algorithms were invented in lots of places, like Georgia Tech and other places, and we are essentially just implementing those in the Bro programming language. So this is what you get for this big library. You know, this is what you're using. You know, you essentially have your bro workers up there at the top. Those are the guys that are just saying, I count you, 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 and they pass those up to reducers, which will then start to take those composable measurements. And then we have this this worker here that basically alerts you when certain epochs and thresholds are crossed to start counting those things over. So this is the general idea, but applying this to reconnaissance detection makes most of these techniques that pen testers and real threat actors are using stand out like a sore thumb. So let's not repeat a slide that I already showed. Let's instead look at DNS. And let's talk about some of the sexy things that we could do from an actual perspective and from a derivative perspective with DNS. So if you're not familiar, DNS is the domain name system. It's used to resolve IP addresses and domain names, as well as a sundry of other purposes. You can ask a DNS server for the reverse mapping, and there's all of these different queries out there. So these are this sample of the problems that you could a measure with this. So a quick measure to see if something was a zone transfer request is very simple. But let's look at these other two. Let's look at what we could get with an NX domain to start. So here what I have is I have DNS Dell internal DNS leak. So let's see what this is all about. Let's start at the bottom of the cake here for this first one, and then we'll skip that later and we'll just go right to the specific protocol log. Excuse me. So we have our tuples here of which hosts are speaking, and you can see here that it's been automatically detected as DNS traffic. And we see this host here, which is my Kali box, sending out a whole lot of traffic to this public DNS server. You can probably ping this right now. Somebody do a look up to it and see what it returns. You ask it for the IP address of Dell.com. It should respond for you just fine. So what the reconnaissance technique essentially involves, and I'm using Carlos Perez's DNS Recon, if you're familiar with that. It's included in all of your Kali distros by default here, is it basically says, hey Dell, publicly exposed Dell server, can you please tell me what is the internal IP address of 10.10.10.10? And sure enough, if you ask it, Dell will start telling you all of the internal domain domains for their desktops. So here you can see that we're mapping out Jabber servers, Federation, servers looks like Australia, DC 2008, America 11. So maybe that's not, what's AU? Anybody have a guess? We could probably figure out what their naming convention is. But this technique comes with a lot of side channel noise. So from a threat perspective, when I approach this problem and decompose it, I start to notice that when you're just blindly asking these servers lots of things, that as a client, you're going to start throwing a lot of NX domains. So let's look at the let's look at the alert first, and then I'll show the code behind it. So here we have actually 2 different alerts that fire. So why would I have 2 different alerts fire? I have one that fires on the client that was doing the work. Why would I have another one? How would you evade this if you controlled like a big botnet? You might start parallelizing your scan. So if you know that I'm detecting, if I'm counting how many NX domains did you have, how many did you have, how many did you have, how many did you have, you might just say, well, you only asked for 10, you asked for 10, you asked for 10, you asked for 10. So what we need to do is to decompose these problems into 2 distinct pieces. The first piece is the client-side attack. The second piece is the server-side detection. And from a summary statistic perspective, it's the exact 2 same pieces of code. So here are the 2 sample measurements that we just looked at for domains. So there's a lot of boilerplate code here. So we're essentially said, whenever I see more than 50 of these things in 10 minutes, let's go ahead and fire off this notice here. And all this other stuff is where I'm saying I want to take a unique measurement, I want to take an actual, whatever. A lot of this is just a simple boilerplate here. But this is the real meat of the code here. So in Bro's event-based. So you have these events firing off as traffic comes by, right? So if you think about each protocol as being a part of a protocol state machine, what we're essentially doing is firing an event at each transition in the protocol state machine. So before you have a DNS reply, you would obviously have a DNS query, right? That would be the obvious approach. So in Bro, you have this DNS query event fire, and then you have this DNS query reply. So this is, what I really like about this little block of code here. If you look at this event when it fires, there's the connection information, there's the DNS message, there's the query that was run, the query type, and the query class. But what's not on there? It doesn't say what port it was on. It doesn't say was it IPv4 or IPv6. It doesn't say was this in a tunnel. It doesn't say all of these network provisioning specific details that as a security practitioner, you may not give a crap about. If you wanted to only detect this for IPv6, you would say in your if statement here in your first line, you would say if IPv6, right? So this is this sort of this power, right? We're abstracting down to what is the base case of any operation, because from a policy perspective, that's where you want to operate. You don't want to have to say, well, let's do one of these for DNS on port 53, but the student network is wide open, so let's look for DNS on port 5353, or whatever the case would be. So we essentially are feeding this in, and the server detection looks exactly the same here. I'm using slightly different thresholds here because a server would commonly be throwing NX domains just as a part of its process, but these are things that you would just need to tune for your own network. So here the observation is we're firing it on a reply, but we're feeding in the server IP address here. Okay, so any questions so far about this? Okay, so let's go back to the presentation. So actually, let's do another example. So that's great. So if we're instrumented, we can take a direct measurement. That's pretty neat, but you do have to be instrumented. But what about taking a measurement where you don't have a sensor? So DNS has this wonderful property where there's the way your network is set up, let's say you have a Cincinnati office and a Kansas City office, that the Kansas City office is going to be recursively sending information back to you. So by only instrumenting your Cincinnati office, you can even start to take derivative measurements about things that are happening where you don't even have sensors set. So in this example, what we'll do is we'll actually look at somebody, let's see here. Is that big enough on screen for you guys? Brett, is that big enough for the video? Great. So in this one, what we're going to do is we're going to actually look at the DNS traffic. And you can see here what I'm doing is I'm sending an ARPA request. So what am I doing? I'm doing a reverse DNS scan. So let's say you're pen testing the Kansas City office, and you want to sweep the network and say, well, tell me what all the names of these servers are, because they're going to be named things very appropriate, like domain controller, DC, VPN, RDP, and whatever. There's a lot of just as part of a standard process, you may do this. Well, as these requests start coming into your DNS server that's locally here in Cincinnati, you can simply start counting an ARPA request. And so a derivative detection that you would be detecting is that somebody did a reverse DNS scan over in Kansas City, and you would even have the IP address that did that. So this is very powerful stuff when you start to apply this to traditional reconnaissance techniques. So let's go to a more interesting protocol than that. Let's go to, I think, HTTP next, or maybe SSL. Okay, so good old HTTP. This is one of your attacker's best friends. If you look at most people now, if you're in a semi-secure or regulated environment, you're going to have like PCI DSS now requires you to have a WAF in here. You know, you have to have a web application filter, and you probably have a next-gen firewall. You got a Palo Alto or something like that. So attackers, though, are speaking valid HTTP and will speak directly through these next-gen firewalls and install things like web shells. In order to do that, they generally need to probe your web applications. So we can start taking a summary statistics measurement based on each specific web app that's running on your server. So the key would be, that for each web app that I see, let's go ahead and count some properties here. So common tools that you may use if you're using Kali or that you would see in your network might be Dirbuster or Burp or SQL Map. They all have this capability. One of the first attacks that we would look at, let's look at URI brute forcing. It's very common. It's essentially where you say, hey, does liamrandall.com/admin exist? Does Joomla? Does WordPress? Does CGI? Yada, 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 all the way down. So the measurement, what the server is going to be throwing is a lot of 404s. So a simple measurement for that would be to take somewhere on here, I have my code. There it is. We'll just go out to the command line and we'll look at the actual traffic sample. So that's basic auth. Here it is, brute forcing. So let's just look right at the http.log. So here you see me going to this website and saying, does accessibility exist? Does Go? Does Betsy? Does text? Does talk? Does toolbar? And we see the web server starting to throw a large number of 404s. Now, just seeing a lot of 404s may not mean that there's reconnaissance, but these summary statistics have all of these other use cases besides just reconnaissance detection. You can know that a web app is now misbehaving on your network, or perhaps that it's overloaded, and feed that information back in. Either way, this information is statistically interesting. So the notice that you would then be firing would be that, hey, again, decompose the problem into two specific measurements. The first one watches by client, the second one watches by server. So that is pretty straightforward. And let's do basic auth. If you're still running basic auth, maybe you have some old web apps that are in your network. You might see somebody, here I'm going to browserspy.dk, and if you look in this column here, you see I'm throwing a lot of 401s, right? And my threat actor is using the username test, and they eventually come down here and they start to, they get a successful logon. They've brute forced the password. Now, the reason why I showed that example not because that's interesting, but because there is a secondary type of measurement that you can do. You can reprogram Bro on the fly. So once I've detected someone that has a specific type of behavior, whether it's SSH password guessing or HTTP based URI brute forcing, you could add them to a whitelist or a blacklist and say, well, we have a known brute forcer. And then if I see them later get an authentication, I have a now derivative measurement that I have detected you doing something that is not good. Maybe you're doing DNS scanning and then you get a successful authorization. That I now have a successful logon from a known brute forcer. And those scripts are actually in Bro for SSH and a number of other protocols. So does this help you on your network when you go in to secure these things? I keep on dropping out of my presentation. I'm skipping over some of these over here. Maybe your network is secure. You're running everything under SSL. It wouldn't be detected as HTTP because you're tunneling it through. So are there other attacks that you could have, or do threat actors leverage these techniques against our own infrastructure? They absolutely do. When you look at the rise of things like T-Bot, or even Tor usage on your network, you start to see things that, well, if I allow HTTPS out on 443, suddenly now people in my office have the ability to go out to Tor. So we can use these techniques, though, to start doing one first, and we'll look at the measurement that we're taking because it's actually a more interesting protocol-based measurement here. So in Tor traffic, essentially what you have is you have a lot of SSL certificates being generated. And we understand SSL, and I don't know whether you know this or not, but when you speak SSL, you say, hey server, let's speak SSL. And you reach out and you have this nice little handshake, and you exchange something called an X509 certificate in the clear. And that X509 certificate is what, if you've ever bought you've gone to cheapcerts.com or, cheapSSL, whatever it is to get these certs, you fill out all of these little properties on your form. What's my common name? What's my domain name that I'm securing? What's my address? All of that information is in here, and we're parsing that out for you. As well as, you pick a cipher. Here I've picked TLS. I'm using diff-Hellman exchange. So even if I had the key there, Control-C, I don't know what the hell I did there. And we'll just, there we go. All right, well, there we're out. So if you look at the way SSL or Tor generates its SSL certificates, this is something that we wrote for an investigative agency, and it's on our GitHub. You can actually download it. What this will do is actually start taking summary statistics of these anomalous type SSL certs and start to take out of nodes that they don't publicly disclose. Time has elapsed on them. But you can see that we can tell you with a very high degree of confidence that you're running Tor. But these aren't the only use cases for these. When you talk about reprogramming Bro, there's actually, almost at it. There's actually some very powerful measurements that you can take. So the next one we're going to look at is not this Lucky 13. We're actually going to look at a web shell called China Chopper. And the China Chopper PCAP, we'll just stay with traffic on this one. Out here somewhere. Okay, here's what China Chopper looks like out on the wire. Okay, so it looks like a regular HTTP request. I'm not picking on a particular threat actor here. The web shell itself is actually called China Chopper. So what you see is you'll start seeing a large number of these post requests to your server. So most people are familiar with getting, the get method of HTTP. A post request is where the client takes a file and uploads it to you. So how these threat actors are evading your next-gen firewalls are, they're just implementing their C2s over the protocols that you do allow. So if you allow HTTP and this gets to your Palo Alto goes, hey, this is syntactically valid HTTP. There's no monkey business going on here. Let's go ahead and pass this back to the server, and they'll start driving your web server and your DMZ and have it pivot to your network. So what we did is we did a heuristic where we essentially use a sum stat to feed this logic. And when we detect a client that is generating too many post requests, we use the anomaly detection approach to say, hey, let's take a statistical measurement. What are most clients doing, and then what are you doing? And then we enable a second dynamic C2 decryptor on the fly. So we can decrypt the C2 in Bro and write it out to a log in real time. And this is what the detection looks like. So we were actually out, that's actually the APT version of it. So we were actually out at a Fortune 20 doing a demo. And we had the China Chopper heuristic fire. And we're like, hey, this looks like China Chopper. But the decryptor didn't work for it. And when we went in and looked at the monkey business part, this is inside the post request, you see these Z1 equals, the command I want to send to the server, Z2 equals, the next piece, Z3 equals whatever. And the decoder wasn't working, because this particular client had a very large signature-based detection infrastructure, and they had deployed a signature that looked for these types of requests in their post request. So this was a powerful heuristic that we were seeing. And when we looked at the contents of the post message, we're like, well, that looks like base64 decoding. So we changed this one little line here, and we said, okay, well, just try to base64 decode it, and let's see what comes out the other side. And this is what we see. The actual C2 commands that are being sent to the web server in real time. right? And what alerted us to this? Our ability to count at scale. It sounds like such a simple idea, but it is essentially so tremendously hard, and that's why other things don't do it. It's this power of the Bro model where you're load balancing traffic to friends, and friends can share information and communicate with each other like a bunch of little girls in grade school. I don't know that I've ever made that analogy before, and I don't think I'll reuse it. You have to try out new things. That's how you know how things suck or not. Right? So I'm going to show you 4 PCAPs here, and we're just going to take the idea of counting. There's a lot of information that we're sending out today, and then I'm going to end with a story. And I'm going to show you just the count of state transitions in these protocols. If you're not an SSL person, you just say, well, 3 of these are normal PCAPs, and 1 of them is an attack. And you guys just take your time and tell me if any of these look odd when you can start to count things like this. Anybody want to take a guess? Number 4. Okay, so let's see what it is. So the first one is a standard Gmail session, right? I can't decrypt that traffic, but just watching from a flow perspective what the SSL state transitions look like. And we can tell when we're doing state transitions in the protocol. We can detect heartbleed, for example. We have a heartbeat event. So the third one is one of those little RSA keys. Those are commonly deployed as SSL TLS. And the last one was the Lucky 13 attack from 2 years ago. I have a similar detector for Beast and all of these other advanced attacks. So does this matter, right? Does this matter for you on your network? Do you need to do this, or is this something that would be of interest to you? And this is where I end with one of these great stories that you usually only get to hear this after 5 or 6 beers, right? And let's talk about something that for a long time we couldn't talk about, which was now known as the Carna botnet, but at its discovery time was called the alien worm. So we have this infrastructure, or rather this infrastructure is deployed very heavily at places like Lawrence Berkeley National Lab and in the Department of Energy. LBL actually sponsors a number of our team members. Most of our team is right out there in Berkeley, right at the foot of the hill where this lab is. So this is this brilliant analyst out here, a good friend of mine named Ashish, and he is incredible. If you go to bro.org and start watching videos, he's like one of our usual suspects at our conference. He always presents interesting things. So the big idea is that we have these, we've weaponized these tactics at certain locations so that as soon as we detect that first bit of reconnaissance, think back to the kill chain. As soon as I detect you, bam, you go in a corner. You're not even allowed to come on my network anymore. And I put you in there for 15 minutes. And then if you come back, you go in for an hour. And if you come back, you go in for a day. And we've equipped and set up these sensors in such a way so that they can actually do things like inject BGP routes or insert ACLs directly into key pieces of network infrastructure. And it is a very advanced technique. The big idea here is that we use our IP space then as a network telescope. Right? We're using it to measure what's going on the internet at large. We can detect persistent scanners and so forth. So we started to have this really suspicious behavior where we would normally see a threat actor or a particular worm go, are you running MySQL? Are you running MySQL? Are you running MySQL? Are you running MySQL? Are you running, whatever it is. The same type of behavior. And we tracked the number of ACLs inserted per day. We started to notice a very rapid uptick, which for us could be a problem because things like Cisco 6509 can only take so many ACLs before they start falling over on their faces. And all network infrastructure has some point. I'm not trying to pick on Cisco here. And more importantly, this was unlike anything that we had seen before. And this threat actor, one day we would see a device scanning for MySQL, the next day DNS, the next day probing SSL, and so forth. And this seemed to be an internet-wide phenomenon. So we started to do some reconnaissance. And this is what the actual kit that looked like on these devices. You could see that there was, it had been compiled for these embedded devices. They'd compiled for like 19 different versions of the same device, and I'll show you the device at the end. They claim, if you go to Internet Scan of 2012, that they were only using default passwords, although I think that we have demonstrated that there were some other techniques that they did not disclose themselves. And they actually dropped a little README file in here that said, hey, this is not malicious that I just took over your device and I've basically turned it into a part of a scanning botnet. And you can email me at internetscan@gmail.com to talk about it. So these guys were pretty ballsy. I don't think that you're here because I think I know who you are. But wherever you are, if you ever watch this video, I think you have balls the size of steel. And you'd probably be pretty easy to pick out from the jingling when you walk in the room, right? So this is what they wrote. There's their little language. So these guys are not afraid of what they're doing. And this is what the botnet was actually made up of. We tracked it back to one Chinese OEM. And it was all of these little crappy security systems that you may have deployed watching your baby or in your office or in your backyard. You can buy these things at Best Buy or Amazon.com. And there was a really scary period when we first came across this information and traced it back to one Chinese OEM of, are these things coming this way by default, or do they just really suck at Linux? And it turns out we think they just really suck at Linux. That point aside, this was a really enlightening thing for a number of people. When you're walking around your network and you're looking at these things, you have to do that grade school thing where you cut somebody's head off with your thumb. You guys ever do that? You're like squashing your head, that. Take everything plugged into the network and don't see the business end, the camera piece. See the Linux box that you're not managing on the bottom. Copying machines, threat actors love those. And the great thing about these summary statistics and reconnaissance is because we're attacking the problem at the protocol level, you have insight into all of these devices. So at this time, I think I'm going to open it up for a couple questions. That was the actual Carna botnet, what it looked like. If you'd like more information about the Carna botnet, or the, as I shall always fondly recall it, the alien worm, you can go to Internet Scan of 2012 to find out about it. And there's loads of information at bro.org about summary statistics if you're interested in following up on that. So are there any questions at this time? Anybody? Did I do that good of a job explaining the material? OK, well, I sincerely appreciate your time. Thank you very much.